So our first speaker today is Elchesen, who will be talking about universality of the Wasserstein distance.
Thanks, Elkanan. And I'd like to thank the organizers for organizing and allowing me to speak. So I'm going to be talking about a universal property of the Wasserstein distance. This is joint work with my advisor, Peter Bubenik. So what we do is we give an algebraic characterization of the P Wasserstein distance for each P from 1 up to and including infinity. And so this takes the form of a diagram functor, dp, which takes as input metric spaces and outputs its space of persistence diagrams, which I'll define, equipped with the P Wasserstein distance. And so the main result is that this construction is universal in a sense that I'll describe. And this result allows us to characterize the P Wasserstein distance as the largest P subadditive metric on the space of diagrams, and I'll define that, of course. So as an application, we get completely formal proofs of converse stability type results. And then if there's time, I'll talk about some extensions to things we call virtual persistence diagrams, which are like signed persistence diagrams, and also to signed radon measures. Okay, so the motivation, of course, is what I'm calling classical persistence diagrams, which everybody else would just call persistence diagrams. So these are multi-sets of points in the half plane above the diagonal. So y value bigger than or equal to the x value. For us, everything's going to be finite. So these are going to be finite multi-sets, but you can extend everything to infinite persistence diagrams. And so the goal is going to be to define a distance between these objects. And it's going to be a matching type distance. So you're allowed to match points in different diagrams. And the problem is that, or the issue that comes up is that different diagrams can have a different number of points. And so you allow yourself to match the diagonal. And so for technical reasons, diagrams are often defined to include all of the points on the diagonal taken with infinite multiplicity. And so our goal is to define persistence diagrams algebraically. And in doing so, we want to bake in this idea of adding points on the diagonal. So that's going to motivate our definition of persistence diagrams. Oh, it did the thing where it didn't move. Okay, I got to reshare. Okay, sorry about that. So we're going to redefine persistence diagrams in the classical setting. So persistence diagrams are elements of the following quotient monoid. So let me set this up. So for a set X, d of X denotes the free commutative monoid on X. So the free commutative monoid, its elements are just finite formal sums of points in X. And actually, these are just equivalent to finite multisets on X, with the monoid operation just being addition of finite formal sums. And so what we do is we just take the free commutative monoid on the upper half plane, including the diagonal, and then we mod out by the free commutative monoid on the diagonal. So here's just an example of a typical element of that space. So, you just take 2 points in the plane and you add them together. And that's a typical element, but really it's a coset in this space. And so modulo the free commutative monoid on the diagonal, you have this equality. So I'm allowed to take any formal sum and add points from the diagonal as many times as I want, right? So we always have this equality modulo the diagonal. And sort of that's baking into this definition the idea of having, being allowed to match the diagonal. Okay, so let me generalize that a little bit. So given a pair, x comma a, where x is just any set and a is a subset, a persistence diagram on that pair is an element of the quotient monoid, d of x mod d of a. So same idea. And an important special case, which is the setting we'll be working in, is when a is a single point. So in this case, we drop the brackets around x naught, and we just write d of x naught. So it might seem abstract to work in this generality, but actually some other things that come up in TDA are actually examples of persistence diagrams in this with this definition. So barcodes are persistence diagrams on the set of intervals of R, with base point being the empty interval. Okay, so kind of a interesting mix of terminology, but that's exactly what they are in this framework. And then if we let rect denote this set of n-dimensional rectangles, which are basically just boxes in Rn, then finite rectangle barcodes, as introduced by Bjurkovic, these are persistence diagrams on the set rect, with the empty rectangle being the base point. Okay, and so before I move on and define the Wasserstein distance on these things, I want to sort of introduce a simplification, which is that we can always take a pair like x comma a and quotient out a and just get a pointed metric space. And that's going to simplify things a lot, and it'll turn out that that's completely equivalent. We can always work in that specific setting. So given a metric space x and a subset a, the p quotient metric for p in 1 through infinity is the following metric space. So x mod a we get just by basically collapsing a to a point. So as a set, it's just the complement of a union a single point, which we also denote by a. And then the metric we define on this is dp, and the way we do that is, so we have x, we have a. So if we have 2 points in the complement of a, so this is a, so their distance is so it's the minimum of the following two things. So you either look at the original distance between x and y, or you match x and y to a. So you take the distance of x and y to a, you put those two numbers into a vector, and you take the p norm. And so the quotient metric is the minimum of those two quantities. So that actually defines a metric. And so given a metric pair, so a metric pair just being a metric space with a chosen subset, we obtain a pointed metric space in this way by modding out by a and equipping it with the p quotient metric. So going forward, we're going to work exclusively with these pointed metric spaces, and this is justified by the isomorphism. So this is a monoid isomorphism. So diagrams on x comma a are isomorphic to diagrams on x mod a, with the base point being the image of a under that quotient map. So that's going to simplify the definition of the Wasserstein distance. Okay, so now our setting is pointed metric spaces. So given a pointed metric space, suppose we're given two diagrams, alpha and beta. So alpha and beta are just finite formal sums of points, but really, so they're cosets of finite formal sums of points. So alpha and beta have length n and m respectively. So we're going to pad those out so that they have the same length. So we're going to add m copies of the base point to alpha and n copies of the base point to beta, so that they both have length n plus m. And these equalities are true mod d of x, not, right? So these equalities make sense because we're working in the quotient monoid. Okay, and so now the p Wasserstein distance is defined as follows. So it depends on d, the metric that you choose on your original metric space, and it's defined as follows. So given a permutation on n plus m letters, you match the ith summand of alpha to the sigma ith summand of beta. You do that for all I, you put those into a vector of length n plus m, and then you take the p norm of that vector. So that's the cost of your matching. And then you minimize over all possible permutations. Okay, so I mean, so it should look very familiar to how we normally define the Wasserstein distances. So you're just kind of finding some bijection between the summons of alpha and beta, and then you're defining this cost by looking at the distance and taking a p-norm, and then you're minimizing over all possible bijections or matchings. Okay. So, right. So I want to, in this setting, describe a universal property for this framework. So for pointed metric spaces and the Wasserstein distance. So before I do that, I just want to remind you about Lipschitz maps and some notation that we use for them. So a Lipschitz map between two metric spaces. So a map F is K Lipschitz if the distance of the image of X and X prime in Y is less than or equal to K times the distance in X between X and X prime. That's probably familiar. The Lipschitz norm, denoted like as a norm sub lip of F, this is the smallest such K. Okay, and in particular, we're going to be interested in one Lipschitz maps. So these are non-expansive maps, meaning F doesn't increase the distance when you map into Y. And now let me define the objects that we're interested in. So we have this universal property that the p Wasserstein distance is universal for some class of objects, and this is exactly the class of objects we're interested in. So a p subadditive metric monoid is a commutative monoid N, which is also a metric space, and for which the monoid operation and the metric are compatible in a certain sense. And that sense is that this equality is satisfied. And maybe let me explain that a little bit, where this comes from. So what's going on here is that addition on N is a map from N cross N to N. And so there's many choices of metric that we can choose on N cross N, but one choice is, I'll call it capital D sub P. And the distance between a tuple XY and X prime Y prime is just defined to be exactly what's appearing on the right-hand side of this inequality. So D of X, X prime, D of Y, Y prime, and then P norm of that vector. And so this condition is exactly saying that addition is one Lipschitz with respect to this product metric. Okay, and an example of such an object is the one we care about. So the space of diagrams on a pointed metric space together with the p Wasserstein distance is a p subadditive metric monoid. So now I can state the universal property. So it's exactly that the space of diagrams with the p Wasserstein distance is the free p subadditive metric monoid. Okay, so in more details, that means that for any other p subadditive metric monoid N, and one Lipschitz map from X to N, which preserves the base point in the sense that X naught gets sent to the 0 of N, there exists a unique Lipschitz monoid homomorphism phi tilde extending phi. So in other words, such that the following diagram commutes, and I didn't define I yet, so what is I? So I is the canonical inclusion, or the universal arrow, so it takes X into dx x naught, and it's given by taking a point in X, so X is going to go to X, right? So so on the left, X is a point, on the right, X is a formal sum with just one summoned. And note that also X naught, so it gets sent to X naught, but remember these are cosets in this quotient monoid. So this is actually equal to 0 modulo d of X naught. So all of these maps here are base point preserving in the sense that X naught gets sent to 0. X naught gets sent to 0. X naught, so by phi, X naught gets sent to 0 by I, and then phi tilde is a monoid homomorphism, which is required to send 0 to 0. So everything's base point preserving, Lipschitz, and phi tilde is a monoid homomorphism as well. And moreover, the Lipschitz norm of phi is preserved. Okay, so let me state this categorically before I give some applications. So let met star be the category whose objects are pointed metric spaces and whose morphisms are base point preserving one Lipschitz maps. And then by CMON met star sub P, this is the category whose objects are these P subadditive metric monoids with the base point chosen to be 0. And the morphisms are base point preserving one Lipschitz monoid homomorphisms. Okay. And this base point preserving condition is actually redundant since monoid homomorphisms always map 0 to 0. Okay, so an analogous way of, a completely equivalent way of stating the universal property that I just stated is as follows. So there's a forgetful functor from metric monoids to pointed metric spaces, and all that does is just forget the monoid operation. So you send MD0 plus to just MD0. So 0 gets chosen as the base point. And going the other way, we have this diagram functor, which takes a pointed metric space and sends that to the space of diagrams with the P Wasserstein distance. And so the theorem, which is completely equivalent to the universal property I said before, is that dP is the left adjoint of this forgetful functor. So we have this adjunction, and this is a very concise way of stating this universal property. Okay, so now I'll just give some quick corollaries. So suppose we have a pointed metric space, and suppose that rho is any P subadditive metric on the space of diagrams, satisfying this inequality. And all this inequality is saying is that, you know, we have this canonical inclusion from X into the space of diagrams. But instead, we can equip the space of diagrams with this metric rho. And so this condition here is just saying that the canonical inclusion is one Lipschitz with respect to rho. So if we have that, then rho is less than or equal to the P Wasserstein distance. So in other words, WP is the maximal P subadditive metric for which this canonical inclusion is one Lipschitz. And so as a corollary to the corollary, which I call the theorem, we get a very abstract form of converse stability type results. So suppose you start with a pointed set, which you don't necessarily care about the metric on it, or maybe you don't have a metric on it. And suppose that you have a P subadditive metric on the space of diagrams. Then you can pull that metric back. So I star rho is the pullback of rho onto X. And then the theorem is that rho is less than or equal to the P Wasserstein distance, which you construct using the pullback. And so this follows actually immediately from the previous corollary. So what do we do? So what is I star rho? So I star rho of XY is just by definition rho of I of X, I of Y. So let's just define D to equal I star rho. Okay, then automatically we just have that this is equal to D of XY. So in other words, this condition up here is automatically satisfied. And so rho is smaller than the P Wasserstein distance that we get that way. Since I have a couple minutes, I can say, well, I mean, why do I call this converse stability? So if you look at the interleaving distance on persistence modules, you can actually view that as a metric on the space of persistence diagrams in the plane. Okay, just by identifying finite decomposable interval modules with persistence diagrams in this way. And then it's straightforward to check that. So DI is infinity subadditive, and I star of DI is equal to, so it's L infinity, but it's the quotient version, right? So we do L infinity, but we quotient out by the diagonal, so we get this quotient version of L infinity. So then this theorem is telling us that the interleaving distance is less than or equal to W infinity of L infinity sub infinity. But this thing right here is exactly the bottleneck distance. Okay, so we get, I guess, maybe the less interesting side of the isometry theorem, the easier side to prove, but we get it completely formally in this way. And this also holds for rectangle barcodes. We can get a similar result. Okay, so that's mostly what I wanted to talk about. And I just wanted to say that, so these ideas extend to other settings. So infinite persistence diagrams with finite total persistence, those are just the Cauchy completion of finite diagrams. And so by sort of composing our universal property with the universal property of the Cauchy completion, we get that the space of infinite diagrams is the free complete piece of additive metric monoid. So there's an analogous universal property there. Virtual persistence diagrams are just elements of the free abelian group K of X mod K of A, K of X being the free abelian group on X. So in this case, the one Wasserstein distance extends universally to this space. So these are like persistence diagrams that can take positive or negative multiplicity. And this gives us the free metric abelian group. And then similarly, the one Wasserstein distance, we showed that this extends universally to signed radon measures. And that's all I have. I just switched to the thank you slide, but it didn't work. So that's it. Thank you. I'll take any questions now.
Thank you so much. Please unmute yourself and applaud Alex. So are there any questions for our speaker?
There it is.
Alex, I had a question on slide 10. I don't know if you're able to move your slides again. There we go.
There we go. Yep.
I was wondering if you could interpret the last sentence, the Lipschitz part for me again.
Yeah, so just that, so the Lipschitz norm is preserved. So, right, I mean, so all these maps are one Lipschitz. So, but, you know, phi could be like 1/2 Lipschitz. And then this is just saying that phi tilde is also 1/2 Lipschitz. So the smallest Lipschitz constant for phi is also the same as that for phi tilde.
Okay. It's a nice mix of category theory and, you know, metric structure.
Yeah, so we're like kind of combining like algebraic and metric properties at the same time. Yeah.
Thanks.
Mm-hmm.
I actually have a pretty general question. Tell me if you can tell me if it applies or doesn't. So in this construction, you have a metric space, which is sort of, there's a single point in it.
Mm-hmm.
And I guess intuitively that's somehow corresponding to the diagonal.
Yep.
What happens if you had multiple points? In other words, you weren't just allowed to include points on the diagonal, but there were maybe other regions of the persistence diagram where you would say, okay, that region is, you know, equivalent to nothing. I'm allowed to add points there for free. You would get presumably some new kind of construction where you can add things. And do you think you would get a similar kind of universality result, or what do you think would happen for something like that?
Yeah, no, that would definitely work because, you know, so this works in the generality of taking an entire subset and then collapsing that subset down. So yeah, you could totally take as many points as you want in the plane and take that as your subset A and do everything in that generality.
So in this setting, actually, I'm thinking you collapse subsets, but you have to collapse them separately. So
I see.
There, maybe you have different regions in the persistence diagram, and you can add as many points as you want in either, but they're not equivalent.
Mm-hmm.
You adding point in one and adding a point in the other are not the same.
I see. Yeah, I mean, you know, I don't know what that would look like exactly, but I think that does sound like something that would be doable in some way. Yeah, you might have to look at like, you know, if you wanted 2 points, it might be like bi-pointed metric spaces or something like that. I don't know, but yeah, I mean, it sounds like something that could be done in this setting.
Would you need somehow two different notions of zero?
Yeah, that's kind of interesting.
I guess the intuition I had is that so when we work with persistence diagrams, we assume that things in the diagonal are, you know, you can add them and subtract them. They're basically trivial. But there could be settings you can imagine in which like other regions of the persistence sort of the diagram could also be trivial. Maybe, you know, from the construction you have, anything born before a certain time is, say, somehow trivial.
Right.
But maybe that doesn't fully really overlap with the diagonal. So you can you can match it with the diagonal, or you can match it with that trivial region, you know, of early birth times, but it's a different region somehow. They're a positive distance apart. Anyhow, it was just an idea. I'm not sure anybody.
I mean, it actually sounds like a good idea, and I think it's something we might have even like thought about once or twice. But yeah, it's not a bad idea. I mean, you could definitely see a situation where you might want to disregard certain information in the persistence diagram, and this might be a way to do it. So we'll think about it more and maybe
yeah,
well, if we
really interesting talk. Thank you.
Thanks.
Any other questions for the speaker?
Yeah, I wanted to ask, so thank you for the talk. I really enjoyed it. Can you do the opposite? So what if I don't want to collapse the whole diagonal?
So do you want to collapse part of the diagonal, or you just don't want to collapse it at all?
Let's say I think that the element near the origin are really noisy, but the things that come later on the diagonal are not so from the noise.
I see. Yeah, I mean, it kind of sounds similar to Elchenon's question.
Yeah, it's the opposite.
Feasibly do that, yeah. Yeah, I mean, you might be able to do that. I mean, these are great questions. I think it'd be interesting to think about these things and see if it would fit into this framework.
Okay, thank you. Thank you.